And this is a specific heat. In other words, we call the heat capacity. And this problem says the water, specific heat for water is, we call C, that is 4.184 joule per gram degree C. This is a very old notation that people have found out. Do you know what this one is? This is also known as 1 calorie. The calorie was defined that if you have a 1 grams of water, how much heat do I need? How much energy do I need to raise up the temperature of the water by 1 degree C if you have a 1 grams of it? If you double the amount of the water, you need twice as more calorie you need. If you want to raise the temperature by twice as much, then you need twice as much. So this is showing this with the question. And the question is, how many grams of do you need? And the temperature is 25 grams to 35 grams. So delta T here is 10 degrees C. So I want to raise the things by 10 degrees C. And what is it? The heat released from, and this is for the water. And the specific heat for ion, this is water, and the C for water, the ion Fe is small, 0.4498 joule per gram degree C. Okay. So the first scenario here is, I remember this problem now. You are going to put ion here in water. Okay? And the ion is 85 grams. Okay? And the temperature is there at 85 degrees C. And in the beginning, the water is 25 degrees C. So we are putting the hot temperature of the hot ball into the cold water, and this one essentially raise up the temperature. Then it's going to have the temperature of this one will go up, and this one will be eventually 35 degrees C, and the Fe. So what that means is the heat will leave and enter to the system. That's a simple heat transfer issues. And when you are when you're in the junior, you will see actually how the temperature profile is changing as heat transfer issues. We are just considering that what is the net amount of the heat that you need, and then you're going to figure that out. So what am I going to do is, as far as the heat for Q, for Fe is concerned, and my heat capacity is 0.4498, and then I have 85 grams, and my temperature is 35 final before 85. And this one allow me to say, okay, that's a minus 111911.65 joule. Okay. So this amount of the heat is leaving from the ion and dumped onto the surrounding, which is their water. And water has, I don't know the mass, so this is essentially X gram. So this amount of heat, as far as the water is concerned, Q water, I am going to switch the sign because water is receiving the energies from ion. So that will be my sign. And then the X heat capacity is 4.184 X grams. And then what's my temperature? Is 35 minus 25, which is 10 degrees C. So that's 10 degrees C. This is 10 degrees C. Okay, so by doing so, you are going to say the x gram is it's nothing but 1911 65 4.1 is 4. So I got it right. And that's for 45.7. Okay. It should be okay, right? So the concept here is you are putting the high temperature ball onto the cold temperature water. Eventually they become the same temperature. And when there is a hot temperature to be cold temperature, some amount of heat has to be lost by the system. So there's a negative heat leaving the system. But as far as the water is concerned, they are receiving the heat. So it will be a positive work, positive heat. And then you can calculate the relationship about heat versus temperature rise and the amount of the mass that you put it in using the heat capacity or specific heat information. You know what specific heat means? Specific means normalized by its own mass. This is a scientific notation. When people say specific means actually per some mass unit, and that's a heat capacity. This room has a heat capacity. This building has a heat capacity, right? Because of the amount of energy to heat the building versus heat this room is not the same because the amount is not the same. So then it is not an intrinsic property of the matter. So therefore you have to normalize by the amount. And the choice for the specific is a per unit mass, which is a gram.